Nicoleta Morilova and I prepared this quick presentation for you here to see what's going on. First, I will try to make a quick introduction of the activities of the International Atomic Energy Agency. Just in general, what is our goal, mandate, and assistance to the member states. Look at this map. It illustrates like the availability of energy and electricity for the people who are living in our planet. So you might see that 2.6 billion people rely on biomass, which can be, of course, considered as renewable energy, but still it's an old source which does not allow this comfortable life and to develop the industry and to improve to sustainable life and development in their countries. 1.3 billion people have no access to the energy at all, and while 1 billion people no access to the health care due to the energy poverty, because they don't have enough access to the energy, and as a result, they don't have access to the appropriate proper health care. This is a problem in this world which is separated by nations, and rich nations, I say poor nations, developing nations, they should work together to solve this problem if you want to live this in peace. So what nuclear energy and nuclear power can offer today for the world development of this? Now, in 2020, we don't have latest statistics, at least I don't have now. Nuclear power reactors generated about 10% of the total electricity generated in the world. I have to say this is a number is less than used to be a few years ago, before Fukushima accident. But anyway, this is a huge amount, and it is a valuable source and sustainable source of the energy. Now in operation nowadays, or maybe like in last year, we had 442 nuclear power reactors, in total power about 400 gigawatt electric. And they were operated in 30 countries. Now we have 52 new reactors, total power 54 gigawatt electric, under construction in different countries, in 15 countries. It includes also 2 newcomer countries. So still countries have interest in nuclear energy and to production. And let me show quickly the prediction of the nuclear capacity. It's IAEA predictions what be done actually in 2014 and 2010. So historically, in this plot, you can see the, I don't know if mouse is moving here, probably. You can see the dark blue is historical production of the, or installed capacity of the nuclear power plants, which reaches more or less saturation somewhere in 2010, about 400 gigawatt electric. And here you have these predictions done by the IAEA in 2010, and then in 2014, the development of the scenarios for 2020, which we can check now, by the way, and also for 2030. You see that in 2010, predictions were much more optimistic for the nuclear energy, so higher than now. But if we look at the, let's say, pessimistic scenario, we have high, low, and high and low scenarios, so-called. If you look at the low scenario and the latest prediction, not latest, but prediction 2014, it predicted more or less exactly within plus minus 5% the projection of the electricity now. So, of course, what I want to say, before, and even like 50 years ago, we were very optimistic about nuclear energy, how it will develop, that will replace a lot of other sources and will be cheap. reliable and sustainable energy source for production of electricity and other types of non-electrical applications for many countries. However, because of several accidents, 3 Mile Island, Chernobyl accident, finally Fukushima, we have this public does not accept this nuclear energy, and we also had to increase safety measures significantly. That increased a lot of the cost of the electricity. So it does make it very competitive with other sources, especially with cheap like coal and gas, and also with now it does make it competitive with renewables. That's why we have this delay from those optimistic scenarios to more pessimistic scenarios now. But we should think, if it will be continue like this, if you really want to fight the climate change, this, from my personal and not only my opinion, nuclear energy provides real clear choice as a clean and reliable and sustainable source of energy for the future generation. So if you look at the projections in 2021, it says, okay, pessimistic, let's say low. We don't say pessimistic. It's low projection. It's the total installed power capacity of nuclear power plants will remain the same, about 400 gigawatt electric. But if you look at the optimistic, let's say, or high-level scenario when nuclear energy will be on demand, we have that in 2050 it will double of the current. But you should also understand this 400 gigawatt and it's 10% now. If it remains the same 400 gigawatt electric in 2050, it will be only 5% of the total electricity production, or energy, we say, production in the world in 2050. Okay. Now let me play one better maybe video. Doesn't play sound here. Okay. Interesting. Moment. Maybe I should play, unmute this system also. No. Okay, let me skip this video then, because I cannot play from Zoom. I know how to transfer the sound. It simply shows the main IAEA activities in the different fields, which is not only energy production, which we devoted our today's workshop, but also it has different application and different fields and a wide area. You will be able to watch this in the next time. I will send you the link, or also from the PowerPoint presentation, or also you can find this information on the web as well. Actually, the International Atomic Energy Agency consists of several departments. The main goal is atoms for peace, means for peace and development, means it was created more than 60 years ago. Idea is to provide, to stop developing of nuclear weapons, let's say, or to freeze, and instead of that, to provide us, the countries, IAEA member states, with reliable technology for the energy production with nuclear energy. Instead of developing weapons, sent to develop this, to use this nuclear energy for the peaceful use for several purposes of peaceful uses. Okay, and then we have Department of Nuclear Energy, which I belong to. We have also Department of Nuclear, I will tell a little bit more details about this department later. We have a Department of Nuclear Safety and Security. This department is really doing work how to provide the rules, regulations, and all things which are required, standards which are required for the safe operation of the nuclear facilities and nuclear power plants and nuclear reactors and all other facilities. We have a department also, Nuclear Science and Applications, which is dealing with all let's say, non-energy production of the use of the nuclear energy, such as isotopic productions, and also several other scientific applications, so like plasma physics for the fusion, for example, for the fusion machines, and several other applications, whatever where you require radioactive isotopes or some nuclear reactions, and this is more or less scientific, and with application to the agriculture, to the medicine, for many other also applications. We have a department of safeguards who are mainly inspectors who control to make sure non-proliferation of the nuclear materials and nuclear, let's say, to make sure that the nuclear energy is used for the peaceful uses, and that's why they call the nuclear, sometimes the energy is called the nuclear watchdog, because they control, they inspect the power plants, check to make sure that no nuclear materials can be distributed and hiddenly distributed to the other places. We have a big department of management that manages this huge, very big bureaucratic organization, and it requires a lot of management as well. And we have a department of technical cooperation, special department, which can accept the money from additional money from the IAEA member states, from the donors, for the specific technical projects developed for others. And I myself and this workshop is organized by the Nuclear Energy Department, when we have three divisions: Division of Nuclear Power, Division of Nuclear Fuel Cycle and Waste Technology, and Division of Planning Information, and Knowledge Management. So here in this workshop, I presented Division of Nuclear Power myself, and Nuclear Fuel Cycle and Waste Technology. We will hear the lectures on this topic. In our Nuclear Power Division, I belong to the section Nuclear Power Technology Development, but we also have International Project for Nuclear Reactors section, and which is doing with strategic planning, how to develop, and scenarios of development of the nuclear energy. You will hear the lectures on this also as well this week. Again, and I have a pleasure to lead the Fast Reactor Technology Development Team, which is a part of Department of Nuclear Energy. Again, just to repeat you, of the Division of Nuclear Power and Nuclear Power Technology Development section. In this section, we are, I don't see the slide, by the way. Something is wrong, but okay. So in this section, we are doing, and let's say, we don't do the research ourselves, but we're trying to share information, collect information, and distribute information about those technologies between the IAEA member states on different technologies, such as including innovative and evolutionary reactors. Evolutionary, I mean, we call this pressurized water-cooled reactors, boiling water-cooled, or generally all water-cooled reactors, including heavy water-cooled reactors, some gas-cooled reactors, and also innovative designs such as heavy liquid metal and liquid metal cooled reactors, sodium and heavy liquid metal both, and also gas-cooled fast reactors, molten salt fast reactors, and molten salt reactors in general, and also including high temperature gas-cooled reactors, and if I forgot something, supercritical water gas reactors, which are innovative and which are the topic of this workshop this week. Okay. So our activities, what we do, as I said, we don't do research there in the agency. What we do, we coordinate research, we collect information and distribute it to the member states. What we call this knowledge sharing. It includes the publishing of the documents on the different topics of the nuclear energy, conducting conferences, technical meetings. Technology development, we coordinate research projects, so-called CRPs, on the several topics which are chosen by our member state countries and who provide experimental data or express the interest in conducting this. We'll explain it a little bit later. And capacity building, which include training courses, workshops, and other documentation, including workshop in Trieste in physics and technology of the innovative nuclear energy system is belong to this activity on capacity buildings. As I said, I personally lead this team on fast reactor technology. It's a small team, getting smaller, by the way. And how do we conduct and what we define, which activities we should choose to conduct here and what we do. For this, we have technical working group on fast reactor, which consists of 20 countries, 20 member states, who are interested in fast reactor technology. Plus, we have 3 observers, international organizations. It's OECD, NEA, Nuclear Energy Agency, and European Commission Joint Research Center, and Generation for International Forum. We will talk about these organizations later. So this is group of the experts nominated by their governments to participate in this activity. And once a year, we have this meeting of this group when the members report whatever they developed in their country, so we know at least what's going on. And also they discuss several proposals and give advice to the IAEA which activities to conduct. The same technical working group exists for the other technologies, including water reactors, heavy water reactors, small modular reactors, and all others. So you can see that we have this, let's say, driving force for our activities by member states due to their representative in the technical working group. And of course, there are other mechanisms as well. So this slide shows the main activities of the IAEA on fast reactor technology in the 2021, previous and this year. This is what I know very well, and I can explain you later in more details. Again, our main activities, what we conduct, and most time and resources consuming, it's coordinated research projects, but also the several benchmarks and other studies. So we recently completed several CRPs, which is so-called sodium properties, NAPRO CRPs. We also completed PSFR source term CRP, PSFR prototype. So, okay, maybe I will tell you later about this. Just to give you the idea, so we have like 2 CRP recently completed. Now we have 3 ongoing CRPs, which I will also discuss. And we have several proposals for new CRPs from the member state that we have to choose which one to conduct. In addition to these coordinated research projects, we are also conducting, let's say, more shorter studies. And as a result of those studies, we issue documents on the topics, on the topicals, to explain what is the status of these technologies or activities. For example, we conduct in 2021, we completed publishing document on benefits and challenges of fast SMRs, small modular or medium-sized reactors. It's also complicated. You will know this story about SMRs later. And on structural materials for heavy liquid metal cooled reactors. Heavy liquid metal means lead and lead visbotectic reactors. We are now just recently conducted technical meeting on development and application of open source modeling and simulation tools for nuclear reactors, which is very, very interesting and new initiative. I will talk a little bit later. Maybe you as a young forces will be interested. I hope you will be interested in this and can contribute and at least study. And we also recently conducted technical meeting on state-of-the-art thermohydraulics of fast reactors. And okay, there are several other activities which I will touch in my presentation later. And one of our important activities, several training courses And here today we have this third joint ICTP-IA workshop on physics and technology of innovative nuclear energy systems. Just not last month, actually 2 weeks ago, we completed the regional workshop on advances in modeling and simulation of thermal hydraulics in liquid metal fast reactors in India. I'm not sure, you participated? No? Okay. This was also, I believe, it's regional workshop. Here it's more or less ICTP organized many worldwide, okay, people coming from all parts of this, let's say, of the world to here. It's very good and very interesting on this. Okay, and we also conducting webinars now, especially after COVID. Webinars became very popular and very effective, actually, also way to brief and to receive very short and effective, easily, also without traveling information on the technologies or something. One of the main activities also is to organize technical meetings and conferences of the IAEA, and this year we conducted the IAEA conference on fast reactors and related fuel cycles, which was fourth in the series of the IAEA conference on this topic. Started in Kyoto in 2008, then in France in 2013, in Yekaterinburg in 2017, and FR22 was originally planned as a FR21 in Beijing, but due to COVID, we have to postpone and make it this in Vienna this year. So we had, for this conference, we received about exactly 365 contributions. We have about 700 registered participants, and of them, 120 participated in person in April of this year. It was the first big in-person event in the IAEA after COVID. Okay, coordinated research projects are like, it could be on the different topics proposed by the member states, and actually this is really research which is conducted by our organizations from the member states under coordination of the IAEA. This usually could be like benchmark exercises when a member state organization provides a specification. Usually it's experimental results, promises to provide experimental results on several experimental tests on the nuclear facilities and nuclear reactors. And participants will do simulations based on the input data and then compare this result with experimental data and also versus each other, so they can adjust, improve their model and simulation tools, improve their models and correct the inputs, and also validate the computer tools for the simulation of the reactors. We have several, and this is actually very interesting. And for me personally, it's also, many of them are very interesting to participate as I did. I will give you one example on coordinated research project on radioactive release from the prototype sodium-cooled fast reactor under severe exit conditions. That was conducted for years. Usually every CRP takes about 4 years, and this was conducted from 2006 to 2020. And this year we published the report. The idea of this CRP, maybe I'll show you on the next slide, was, it's not experimental data, of course. It was originally provided by the EGCAR, proposed by EGCAR in India to conduct the research. What happens with the sodium-cooled fast reactor, similar to the PFBR, prototype fast breeder reactor, which is now under commissioning in India, if in case of the hypothetical severe accident. We say hypothetical because actually the probability of this kind of accident is very low, and it's practically eliminated. What they say, practically eliminated. However, practically eliminate means is physically impossible or very low probability, which is, again, kind of discussion on this. But let's say what happens with sodium-cooled fast reactor if the, due to the, for example, sodium, if you have the kind of fill-off, unprotected loss of flow accident, you have this pump stops, sodium evaporates, you have a positive reactivity feedback, and finally the corium is molten. What happens with this mass of the corium, molten corium, if it reacts with the remaining sodium in the pool? What happens with this reactor? How many potentially radioactive materials will be released to the atmosphere? This is very interesting and very complicated. I think that nobody knows how to, because also fortunately we don't have experimental data, nobody knows how to answer this question, but to try to check between the participants what kind of simulation tools we have, what can we simulate and how simulate it, and to ensure that at least all these radioactive materials are even released from the reactor will be remain in the containment building. It's a question. And also it's nice and interesting verification, I would say, or interesting application of the simulation tools used for the reactor. Here you show in the middle, shows the reactor core, but hypothetical again. And here inside, it started from the molten corium here, and the huge, as you might see here, sodium pool. And let's say when this fuel, molten fuel, interacts with sodium, sodium is immediately evaporate, and there is a bubble growing, and it grows up, and also goes up to the upper plenum, when it means huge masses of sodium again, and then it collapses, condensed back again. Finally, so this is not like simple expansion phase, like bubbles growing and then make a boom, and then it's a transient and very complicated three-dimensional process, which cannot be even simulated in 2 dimensions, for example. As a result, you have the pressure distribution in the upper gas plenum with an also distribution of the radioactive isotopes there. Then you can calculate how much of these isotopes and sodium vapor will be released to the containment from the reactor vessel, and so on. This is so-called work package 1. Just to show you an example. This slide shows another example of the CRP, benchmark analysis of FFTF loss of flow without scrum test. FFTF is fast flux test facility that was working like 30 years ago in 1986, more than 30. Okay. In the United States, and actually they did really, it was not producing electricity, but it's a big sodium-cooled fast reactor with uranium oxide or MOX fuel, unlike other United States use usually metallic fuel, but in this case it was MOX fuel, oxide fuel. So 400 megawatt thermal, but not producing electricity. And it was a loop type plant, because there are sodium and loop type reactors, which we will maybe will be discussing later. One of the features, this is a relatively small reactor core. One of the features of this reactor was, maybe I show you here. Something. It's so-called gas expansion modules, which are fuel, non-fuel assemblies, 6 arranged in the peripheral area of the reactor core. Core is small, also in peripheral area, and that was at the nominal flow due to the higher pressure of the sodium in the inlet of the reactor. The level of the sodium in this gas expansion sub-assemblies were high, but when the flow is lower, it becomes, the level becomes also lower, so it expands and gas replaces the sodium. In this case, because it's opposite like standard, because it's a peripheral area, it adds the negative reactivity. And in this particular test, reactor was working on 50% of power, then the reactor pump stops, and then there was a transient process which, okay, the reactor survived this, probably because they could also check this, and they proved that this GEM, gas expansion model, can effectively shut down the reactor in case of this kind of ULOF accident. The thing was for other participants, which is about 25, to simulate this transient and to predict the behavior of the reactor during this transient. First, in the blind phase, when we knew only the initial conditions and reactor parameters, geometry, and so on, but we didn't know they also didn't know the real experimental data, so-called blind phase. The experiments we compared with blind phase. I don't know, this is maybe too much for. I believe I have a slide for tomorrow to explain this. And every CRP takes about 4 years. Now the FFTF was also completed. Now we are preparing the publication that we will publish in the next year. Another CRP was based on the data provided by China Institute of Atomic Energy, CIA, which is provided experimental data for neutronics benchmark of CFR startup test. CFR is China Experimental Fast Reactor that started in like 10 years ago and operates. And during the startup, they did several standard tests and provided data for the IAEA participants. Again, first in blind phase, let's say, when participants didn't know the data, and then later in the refined stage when they could compare the data. So here the data were general net criticality when you assemble the reactor core. Then contour road worth, it was test temporary reactivity coefficients calculated, sodium void reactivity effect, and several other tests which we conducted. Again, this slide shows the timeline of this CRP conducted in 4 years, which already in November we had the final last research coordinated meeting of this CRP, and I hope we'll publish next year again. We will publish, for this CRP, we will publish, actually planning publish not one final report, but several documents, which also shows how to use the Monte Carlo neutronics code for such as Serpent2 and OpenMC to calculate the neutronics with Monte Carlo method, with example of the CFR of this test. This year we just started a new CRP, which is benchmark of transient from forced to natural circulation experiment with heavy liquid metal loop. This is so-called NACI-UP experiment, which is conducted here in Italy, nearby in Brasimone, not nearby, another site of this bay. In Brasimone, it's heavy liquid metal. Actually, it's lead bismuth eutectic loop. It simulates, again, loss of flow test. Of course, there is no neutrons, it's simply a simple loop which includes one mock-up of the fuel assembly, which electrically heated pins and pump. Then pump stops, and you have a transit which goes through the force conversion. Finally, you have established a natural circulation mode, which is also, obviously, this test section, at least not necessary reactor, survives, which you have about 10% of the power, sorry, 10% of the flow rate, of 10% of the nominal flow rate conducted, which is enough to cool this test section. And it's also provides, it's not, let's say, it does not copy the reactor data. It provides the materials and experiments for validation of the computer codes which are used in the vault for the simulations, such kind of experiment. And this is our first CRP related to the heavy liquid metal, because now lead-cooled fast reactors become also popular. We also conducted recently technical meeting on state of the art of thermal hydraulics of fast reactors. which included many, it was a review after maybe 20 years, what is the new development in this, what is again, what is kind of new experiments, and also the reviewing the state of the art of this technology, modeling and simulation, experimental results for the thermohydraulics of fast reactor cooled by. Actually, it was mostly on the related to the liquid metal, both sodium and lead, but also several gas and several contributions were related to the gas-cooled reactors and molten salt-cooled reactors. Okay, another interesting thing, actually, which I was personally very interested in, it was a technical meeting on development and application of the open source modeling and simulation tools for nuclear reactors, so-called ONCORE initiative, which we started in the IAEA with help of several also lecturers will be explained probably this week on this. Actually, the idea is usually it was in-house code or proprietary codes to simulate the nuclear reactor, such as, for example, MCNP, also every CFD, commercial CFD codes. And, but the new trend also started, can we use the open source approach, open source tools for the simulation of nuclear reactor? And that was discussed on this meeting. The benefits are obvious because it's freely accessible and also easily accessible. So all students, professors, especially for educational purposes, you can quickly access the code, you can run the code, you don't need to apply especially for the licensing and so on. You just use, and also this code itself, or developers of this code, benefit from this because you have more users, users contribute to development of this code for the testing and developing this code, so it becomes popular. And one good example is OpenMC, which is Monte Carlo simulation code for the for the neutronics and the reactors. Another example is OpenFOAM, GenFOAM. There are several branches of the OpenFOAM. OpenFOAM is a CFD code for simulation of everything. Okay, it's just general CFD. But there are several branches which use this kind of CFD codes, open source code for the simulating also of the nuclear reactors. And I'm inviting you also myself, to revisit these pages and to see how can we use this in future. We're also working closely with the IAEA Department of Nuclear Safety and also with GIF, Generation 4 International Forum, and we're conducting every year workshops on safety of the liquid metal cooled fast reactors. Started in 2010. Every year we have an exchange of information on this, on the LMFR safety. It used to be safety of the sodium cooled fast reactors. Now it's more general, includes heavy liquid metal and safety of LMFRs. Okay, one of our important activities is joint ICTP IAEA workshops on innovative nuclear systems. That's very good, like ICTP invited us to conduct this workshop here because they have many connections and experience to propose to, let's say, to select the participants from around the world, from all countries, and collect here in this beautiful place and to organize these workshops. I would like to thank this ICTP for this opportunity again presenting, and now it looks also better. So maybe for the group photo, we can make it. Unfortunately, today I am the only in-person lecture from all lecturers. All others are participating online, so I suggest we can do it on Wednesday, if weather is good, or any other days for the group photo. But we also should make group photo with online participants as well. Okay, we have several simulation tools also which are supported by the agency in our section. One of them is Sodium Properties Calculator, just recently released. It's NAPRO, so-called. You can search for NAPRO Sodium Properties Calculator and find. it's an addition to our big public, to the CRP and publication of the properties of the sodium, which once you can use also in textual form, but you also can check and see what are references for the sodium for the different coolants. And another educational tool, it's educational part of we have a suite of the educational simulators for the nuclear power plants, and in this case, which also I was doing and involved in the activities on educational simulator of the sodium-cooled fast reactor, which is already obtained by the IAEA, by the vendor, and now we are preparing the technical documentation and exercises manual, which can be used for the student. But if you are interested, you can already now request this simulator, and we can distribute it for you for the purposes of the testing and also for the education. Here, this slide shows our main activities in 2020, which was International Conference on Fast Reactors and Related Fuel Cycles in April, several other meetings and other events. And this year, we conclude this joint ICTP-IAEA workshop on physics and technology of innovative NES here in Trieste. I finally would like to advertise that IAEA is hiring the personnel, and to work in the IAEA is fun, and I would like to, you can search how to find the employment, just search this employment at the IAEA, and I invite also young generation to join the agency if you have interest, and to spend several years in Vienna working in support of this nuclear energy in Atoms for Peace in general. Okay, thank you. Thank you for your attention. I also would like to show briefly the workshop program. Let me check the time. Okay, and introduce our lecturers also. So, we will have this, I think you have this program already there. The idea is in the morning and afternoon, we will have the big lectures from our professors and other experts around the world. And in the afternoon and the evening, we will concentrate on the group activities. Means we will be providing you several simple exercises, which we will do in groups. And first of all, please, in the end of this day, let us, or we can also do randomly for you if you like. Or you can also compact in the several groups. Try to make it mix for the gender, for the geographical distribution, not to be randomly distributed, I would say. We have, by the way, very nice gender representatives here. I know, 50-50 from my, I don't count. This is good because we are welcome. We are welcome very much female. In my age, already that unfortunately we have very few female, let's say, experts, because we started used to be, when I started my education, I don't know, 40 years ago, I forgot when already, it was job for the man. And but now, and that's why we have this too many, let's say, or female underrepresented in nuclear engineering in general, obviously, because if you start from 90% or 95% of men, you cannot expect to be 50 women to be representative after this. But now, because now, fortunately, nuclear engineering becomes popular also through the women, and we have special initiatives for this. And the IAEA, International Atomic Energy Agency, supports this. For example, we have scholarship for Maria Skłodowska-Curie scholarship. So those who are working now on the master course can apply for this. If you need more information, you can just ask me directly. If you're on the master course, the first or the second year of the master course, you can apply for this scholarship and obtain this scholarship. This is for the female participants, by the way. Okay. Okay, again, the idea is we will give you several activities, and you can do these exercises in the evenings, especially like now it's no sun, no swim possibilities, so then you can concentrate on conducting these exercises. And the last day, on Friday, we will discuss it every evening, what's going on. You can ask questions, and we just consult. We are planning actually 3 activities. I'm not sure. We'll see how it goes, but you will be informed. So, and the last day, I believe we can do 3 or 4 groups. Also depends on you, as many. And the last day, we will be, all 3 groups will be delivering short presentations on the results. What happens, we will see, compare the results. It's not necessary to be very accurate and precise, because it's too short, and also we understand that you are also working here all the days, and in the evening is maybe not enough, but just to present these exercises, okay? Which will be followed by these group presentations, and then I think Nicola will distribute the certificates for the participation in this event. Tomorrow and on Wednesday in the evening we will have poster sessions. You all, thank you very much, you all prepared the posters which can be distributed there, and we will discuss this poster. We'll have like 2 hours poster session every evening. And we will select maybe 1 or 2 or 3 posters as a best posters, I know that, because we want to distribute as many, the awards as possible here. Then please be prepared to answer the questions. All lecturers will come and ask you the questions. We will have a discussion, and please try to present your poster as much, as possible to deserve this one of these awards. And maybe all, if you have questions about the program, let me know. No? Okay, we can do. Please also, during at least my presentation, please interrupt me. Also, participants from the online participants, please interrupt me and send the question whenever you have chat, put in chat, or raise your hand for online, or interrupt me anytime from here. Oops. Now I have a pleasure to present our lectures that will go as they, not as of their importance, but as they appear in the program. And one of them is Chirayu Batra, who is Chief Technology Officer in Terra Praxis and Liquid Catalyst. He just started this job in this summer. Before that, he was a nuclear engineer and project officer here in the IAEA in fast reactors team, and also in small modular reactors team since 2015-2022. And he has 2 master degrees in nuclear engineering, one in nuclear engineering and another in nuclear reactor physics. And I believe that Shri Batra is now online with us. Chirayu, would like to add something? Maybe you can welcome participants also. Chirayu, can you hear us? God, this is something. Okay. Disappeared somewhere. Anyway, you will see him soon. He was actually supposed to be here in person, but now today he will be also presenting online. Another lecturer, which will be starting this afternoon presentations, is Professor Kasilov. He is the managing director of the Regional Network for Educational and Training in Nuclear Technology, StarNet project. He is also professor of National Research Nuclear University, MIFI, in Russian Federation. He has PhD in nuclear engineering, and his areas of experience is nuclear engineering, education and training, nuclear management, research and development in nuclear technology, international cooperation. He is more than 50 years has experience in the nuclear field, and he used to work in the IAEA Nuclear Power Division, and received in 2001, he received American Nuclear Safety Training Excellence Award, and also published about 150 scientific publications during his research career, which is he still continue. Professor Akira Tokuhira sensei from Canada, Ontario Tech University. He will be also presenting this afternoon. Like he will be presenting online, and since Canada time difference, they all North American lecturers will be presenting in the afternoon and in the evening. He was a dean of students in this Ontario Tech University, and okay, he has great, very long experience of his working in his working list. Appointed in very several United States organization, Oregon National Lab, Idaho National Lab, Pacific North National Lab, and US. Okay, sorry. Okay, thank you for noticing. Thank you for noticing. And he works actually in several appointments. He was also he was born in Tokyo, educated in the US. He got his PhD in nuclear engineering from Purdue University, and he worked also in JNC. I don't see. I met him first when he worked in JNC, now JIA in Japan. Okay, Akira will explain him. And he is also member of Women in Nuclear of Canada, by the way, so he supports effectively women contribution to the nuclear engineering. Okay, so for tomorrow, we will have online lecture from Professor Vladimir Artisyuk, who is now since 2 years, more than 2 years already, is a counselor and advisor to the Director General of State Atomic Energy Corporation, Rosatom in Russia. He is also contributing since 2016 as a member of Standing Advisory Group for Nuclear Energy into the IAEA. Vladimir got his PhD from Obninsk Institute for Nuclear Engineering in 1991 and Doctor of Engineering from Tokyo Institute of Technology in 1997. So he is classmate for our ladies representative here from Obninsk and also from Tokyo, the same. And he was working in nuclear engineering and fuel cycle development in Tokyo Institute of Technology and INP. Professor Adrian Budges is he's professor of engineering physics at McMaster University in Canada, and his specialty is nuclear reactor core physics of different designs, particular CANDU reactors, heavy water reactor CANDU in Canada, and several different other reactors, including the future designs, and especially we inviting him as an expert in supercritical water reactor and molten salt reactors, which are innovative reactors and topic of this workshop. Prior to beginning professor at McMaster, Adrian was the manager in charge of the reactor core design in the ACR 100 at Atomic Energy of Canada. And before coming to Canada, he was professor in experimental particle physics at Utrecht University, participating in scientific experiment in lab and design of experiments at Large Hadron Collider. And he is a fellow and past president of Canadian Nuclear Society. He already delivered lectures 2 years ago, actually 4 years ago, sorry, 4 years ago here in Trieste, and that were very well received here. Another representative of he's Alexander Bychkov from the IAEA. He is senior nuclear engineering expert, and he is working in the INPRO section of the IAEA, our sister section. Before rejoining IAEA 2 years ago, he had a diplomatic post of Rosatom representative to the international organizations in Vienna. From 2011 to 2015, he was served as the Deputy Director General of the IAEA and Head of the Department of Nuclear Energy. Alexander will deliver several lectures, and very intensive lectures, I believe, today. He will be arriving tomorrow. And he was graduated from Moscow State University in chemistry in 1982, and he covered a lot of the areas, and he devoted his life to the nuclear engineering. And he was also published about, and he was a co-author of about 100 scientific publications. Professor Takashi Takata, he will be again arriving tomorrow and starting his lecture on Wednesday. And since 2021, he is professor in Department of Nuclear Engineering and Management of the University of Tokyo. And he is the chair also of the Risk Assessment Technical Committee of the Standard Committee in Atomic Energy Society of Japan and visiting researcher in Japan Atomic Energy Agency. So he's doing a lot of work in this field, and we will see in his lectures, his 2 lectures, probably 3 lectures on the topic this week. He received his PhD from Moscow University in 2004. Okay, Christian Ladje, Dr. Christian Ladje from CIA, former work at the CIA, now retired but consultant in the CIA. He will be again arriving tomorrow and deliver several lectures on the several topics. And after retirement, he is consultant and scientific advisor for CIA in Kadarash. You see, Christian supports in bold. It hit his text also, which okay. And he actually has very exciting and long experience in nuclear engineering and technology, and since 1979, after he completed and received PhD from Institut National Polytechnique de Toulouse in France. He was doing with many, especially on the sodium-cooled fast reactors, and his topic is the sodium-cooled fast reactors. And I'd like to add to this introduction that Christian participated in previous 2 workshops here in Trieste, and this will be his 3rd workshop in Trieste again. Finally, I would like to introduce Nicoleta Marilova, who is supposed to be here, but unfortunately she was not able to attend. And his 2nd year is a nuclear engineer in fast reactor technology development team, working with me. And he also has short but very intensive experience in nuclear engineering since 2016, when he got her PhD from Karlsruhe Institute in Technology, KT, in Natural Sciences in 2022. And before that, he completed his Master Science degree from École Polytechnique Fédérale de Lausanne, EPFL, what we saw, and also in Paul Schredel Institute, PSI, in nuclear engineering. Finally, myself, I told you already that I have a pleasure to work as a team leader of fast reactor technology development team at the IAEA. I also received the PhD from Obninsk Institute of Nuclear Engineering in 1994. It's from, so we are mates also. And again, from Doctor of Engineering from Tokyo of Technology, so also with you. And I worked in IPP in Obninsk, and TTH, Tokyo State Technology in Japan, JNC, which is JEN now, INP on Obninsk, and KIT, Germany, former FZK. And I'm happy to welcome all of you here today and this week in this great workshop. Before we go, I just want to ask if Nicoleta, are you with us?
Hello, can you hear me, Vladimir?
Yeah, yes, we can hear. So welcome. Okay, how do you feel, Nicoleta? I hope you are better. So you can join.
Yes, I'm better. Thank you very much. I'm very excited for this workshop.
Please
add. Sorry, I cannot be there.
Yeah, we miss you. Please add few welcome words to our participants.
So very excited for this workshop. I'm also excited for the lectures in the next days, and I hope you will all learn as much as you also have expected. And yes, so I hope I wish you all a great few days.
Okay, great. Thank you. And then Any questions? Oh, it's perfectly in time, huh? Any questions to me on this workshop in general, on the program? If not, okay. If not, we will have a coffee break, and I don't know if you need a group photo, we can make a group photo also today. Also, boss, please, those who are online, please come at 10:45 here, Italy, Central European Time, means in 15 minutes, and we make a group photo online also as well.
Okay, thank you.